In this paper, we present a method on answering multi-dimensional range queries under the formal privacy guarantee called the local differential privacy. My name is Tianhao Wang. This work is done while Jianyu was visiting our group at Purdue University. Multi-dimensional range query is a pretty basic problem in data analytics. In this setting, each user has a multi-dimensional record, and here we assume the records are all numerical. And our goal is to answer questions like the number of users whose age is in some range and salary is in some another range. And in this paper, we consider this problem under local differential privacy. In particular, in local differential privacy, the true data will never leave the users and never be sent to the server. Instead, before users send their data to the server, the users use a randomized algorithm R, which somehow adds some sort of noise to the user's data, so that giving any pair of two inputs and for any specific output, the probability ratio of observing the two outputs is bounded by e to epsilon. And here epsilon means is a parameter quantifying privacy, and the smaller epsilon means the two probabilities are more close and maybe almost identical, which indicates good privacy because no matter how I change my input value, my output is still very similar. However, this also means bad for utility because no matter how I change the value, the servers will always observe the same output and thus cannot get meaningful information. So to report a multi-dimensional value under local differential privacy, a basic method is to first encode the value into a one-hot matrix where there is only one and all other values are all zeros. The user then add some form of noise to the matrix to satisfy local differential privacy. And then the user send it to the server. Note that during the communication, the user will apply some compression technique, which will be presented in the paper. So the server, after receiving noisy matrix from all users, can reconstruct a result matrix. Here, each value in the matrix can be seen as the true number of users in this category plus some independent and identically distributed Gaussian noise. And note that our example here only talks about a matrix and which involves two attributes, but it can be easily extended to multiple attributes as long as space is not a big issue. However, since noise in this case is IID Gaussian noise, this method will have a large error in two cases. First, to answer a range query, we need to add a continuous region of noisy counts. For example, if we care about number of users whose age is 19 and whose income is below 1,000, we will add two counts here. So in this case, noise will add up, and the error is linear to the size of the range. And secondly, if we care about multi-dimensional query, and if a query involves only a subset of all the attributes, we need to add all the corresponding values in the remaining attributes. For example, here, if we don't care about age, we only care about salary, we need to add all the columns together, and this will also lead to a big add up for the noise part. To handle these issues, we made two key observations. First, smoothness, which means that nearby counts are likely to be close. Second, sparsity, which means there is no high degree correlation within the real world datasets. Most of the correlations are perhaps only low degree, and the high dimensional matrix, maybe most of the values are zeros, and thus is sparse. So utilizing these two observations, we propose a method that focuses only on the most high-level information. In this case, giving a 8 to 8 matrix, where each dot here represents a number. Our method first uses binning to group neighboring categories together so that we can answer range queries more accurately because we don't need to add many estimations and noise will not accumulate. Note that here, if a query spans multiple bins, we assume the data is distributed uniformly within each bin and use that to answer queries. And this utilizes the smoothness observation. To extend this method to multiple attributes, we first partition users to groups so that each group of users will work on one pair of attributes. And then if we want to answer high-dimensional queries, we combine the two-dimensional information using a method which we call multiplicative updates to synthesize the high-degree answer. So we will present more detail of the multiplicative update usage in the paper. So in this case, the low-dimensional estimation only get the low degree correlation, but will not capture the high degree correlation. And this is how we utilize the sparsity assumption. Note that one shortcoming of this method is that if the bins are too coarse-grained, the uniformity property does not hold, and we will have a large bias in our answer to range queries. So to overcome this issue, we propose a method which is a somewhat hybrid between matrix and one-dimensional estimation. So in particular, we append the previous method with a more fine-grained estimation for each single attribute denoted by these green dots. And we will also use this fine-grained estimation to get more precise answers in the multiplicative update to range queries. We implement our methods and open source it on GitHub. One key low-level detail of our method, which I didn't present, is to analyze the errors and find the right granularity of the grids. So we also implemented several competitors, and we evaluated all the methods on several datasets. One common property of all the datasets is that their total domain sizes are all pretty big. For example, we collected some attributes of the American census, also called the PUMS dataset. And in this dataset, each attribute has a size of 2 to the power 6, which is already pretty big. And if the dataset contains like 4 attributes of them, there will be 2 to the power of 24 possible values in the total domain, which is very large. Here we show some experimental results for different epsilon values. Our method, which we call HDG, outperforms existing approaches. We also have similar results for other metrics and other settings. And the audience who are interested are encouraged to read our paper or come to our poster session to discuss more. And thank you. I'm happy to take more questions.